Circuits Lab by Drew Peljevich. Introduction. For this lab, there are three basic physics laws to understand in order to understand the concept of the circuit lab. First is the law of the loop rule. Loop rule dictates that the voltage of a closed loop of a circuit must add up to zero, no matter what loop you choose for the circuit. The law of charge conservation dictates that in a circuit, electric charge is neither created nor destroyed. That means all the electrons that go into a resistor have to also come out of a resistor. And lastly, steady state. In a circuit, steady state is defined as when the system is stable and the current is constant at all points. If you're talking about an RC circuit, this is when the capacitor is either fully charged or fully discharged. In the first circuit, there are two resistors, 47 and 100 ohms, and two batteries of 1.5 volts each. Since the resistors are in series, that means we can simply add the resistance of the two light bulbs together to get the total resistance of 147 ohms. And we can add the voltage of the two batteries together to get total voltage of 3 volts. By doing so, and using the equation V equals IR, we can find the current in the circuit to be 0.02. And using conservation of charge, we know that this is true for all points in the circuit. Furthermore, by reversing the ammeter in the circuit, the ammeter will read the same current, because, using the equation I equals VR once again, we know that the direction of the current flow does not influence the magnitude of the current. A voltmeter placed in the place of an ammeter will return the total voltage of a circuit, because a voltmeter has a very large resistance and so no charges flow through it. A voltmeter in series, however, with the ammeter will return zero, since there is no difference in a wire, because the wire has zero resistance in it. The ammeter remains the same because the resistance in the voltmeter is very high, and so the ammeter reading will still be the total current in the circuit. Here's the voltmeter placed at different points along the circuit. When the voltmeter is placed across the batteries, the voltmeter reads 3 volts, which is the total voltage across the batteries. Over the first resistance, it reads negative 0.96 because the circuit is losing 0.96 volts of potential energy. Furthermore, over the second resistor, the voltmeter reads negative 2.04 volts because it's also losing that much voltage. When you take the total voltage over the battery and add it with the voltage reading over both resistors, you get 0, which is in accordance with loop rule. Furthermore, the voltmeter placed at any other points along the circuit reads 0 because there is no change in potential energy because there is no resistance. Here's a graph of the potential difference across the circuit, starting out at 3 volts, which is the EMF from the battery. The graph goes down slightly over the 47 ohm resistor and goes even steeper over the 100 ohm resistor until it reaches 0, which is also in accordance with loop rule. There is no change over the potential energy over the ammeter because there is no resistance to the ammeter to change the potential energy. Once again, the ammeter does not change reading when the voltmeter is attached because the voltmeter has such a high resistance that no charge flows through the voltmeter. Furthermore, putting the ammeter in parallel, however, does change the circuit because the ammeter has 0 resistance, and so the electrons choose that path instead to make the 100 ohm resistor go dark. On the right side, you can see calculations for the total circuit, using the equation R equals V over I, and using the voltage and the current calculated by the voltmeter and the ammeter, we can calculate the approximate resistance of each resistor. Notice how the resistance of the wire and the ammeter is 0 because there is no potential difference over them. In circuit 2, light bulb originally starts out very bright and then dims out to nothing as the capacitor is charging up to full charge. When the battery is first disconnected, the light once again turns on at full brightness when the capacitor is discharging, and then goes out again as the capacitor discharges. When first connected, the circuit starts at maximum current V equals IR, and then decreases as charge is built up on the capacitor to 0. The same is true when you're discharging the capacitor. The circuit starts at max current and then goes to 0 as the capacitor loses charge. For the 10 ohm resistor, it took 9.85 seconds to charge and 9.82 seconds to discharge, roughly the same amount of time. The same was true with the 20 ohm resistor. It took approximately 18.27 seconds to charge and 18.45 seconds to discharge, roughly the same value. Here is a plot of the natural log of potential difference over the voltage of a battery versus time. The slope of the line is -1, which means that in this case, RC equals 1. What if questions? If the ammeter was real instead of an ideal simulated ammeter, there would be some resistance inside the real ammeter, since no real-life object can have a perfect 0 resistance. As a result, there would be less current in the circuit, because V equals IR states that as more resistance is added, less current, as voltage stays the same. If I used a real battery to charge the capacitor without a resistor, in real life there would be some resistance in the battery, so it would take a non-zero amount of time to charge the capacitor. However, in the simulation, there was no resistance in the wire nor in the battery, and so the capacitor charged immediately. In conclusion, I used an online simulator in this lab to model a circuit under different circumstances in order to understand the relationship between current, voltage, resistance, and capacitors, using my fundamental physics laws and equations.